Hi, everyone. So I'd like to start by thanking the organizers for this opportunity. And today I'm going to talk about a topology-preserved map of space that supports goal-directed navigation. Right, so let's start with the navigation problem. Right, so imagine this animal located at this corner of this environment and wanting to go to this distally located reward. Right now, there's two pieces of information that the brain needs to represent to successfully plan the trajectory, and that is where am I and where do I go. Right. Now, both of these information needs to be persistently represented in the brain so that in the face of an obstacle, a new route can be calculated. Now, this question of where am I is extremely well studied in the field of navigation, thanks to the discovery of place cells and grid cells and other spatially tuned neurons, which help us understand how the brain exactly pinpoints the current location at any given point in time. Right now, however, this question of where do I go is a bit more problematic because in this case, the brain has to represent a location where the animal currently is not present, right? And the third important question in this setup is how far is the water, right? So in other words, where is, what is the distance and direction of the target relative to the starting location, which is actually required for proper action planning, right? Now, this sort of question of how the brain preserves relational information has been asked over the ages and has been investigated by various labs, including Yale's. And but we still don't have a very good understanding of how the brain does it. Okay, now to address the question 2 and 3 that I put up here, we designed this linear track which is 2 meters long, and it has 10 reward locations, right? And to get rewarded, the animal has to alternate between 2 locations at a time, right? So first it licks in well 1, then it goes to well 8 and licks to get water, then it turns and goes back to well 1, right? And so this is how it actually looks. So you can see that the rats are actually quite comfortable doing this, and they're quite like pros actually in this task. So what happens is after a few successful alternation, we give a signal saying that the rewarding well pair changes. So let's say it's now well 4 and 9. So now they have to alternate between well 4 and 9, right? And this continues for 10-15 blocks, and it ensures that the goal is continuously updated. And what we found is that the rats can learn this task within a matter of 2 weeks. Right? Now, as the animals perform this task, we performed high-density recordings from the orbitofrontal cortex. And the reason for targeting orbitofrontal cortex is that I hypothesized that goal representation is like representing the decision of a location, right? And the OFC has been heavily implicated in decision representation. And the second reason is that the OFC has also been shown to encode a structured representation of task states, which sort of links to the relational representation of space. So let's address this first question of how is the goal represented. And so here I'm showing you the activity of a representative OFC neuron in 3 example trials. In the first trial, the animal is going from well 8 to well 2. In the second one, he's going from well 5 to well 8, and the third one is going from well 2 to well 5. So what you can see is that the firing rate of the of the OFC neuron is high when the animal is at location 8 compared to when he's at location 5, right? But what is interesting is that the firing rate of when the animal crosses well 5 in order to go to well 8 versus is very different compared to when the animal is actually approaching well 5 as the goal, right? This is in stark contrast to, let's say, a hippocampal place cell where I'm showing 2 example trials. So you can see that this cell fires always in this particular location irrespective of where the animal is actually going to, right? So this implied that the OFC neurons probably has some information about where the animal is heading throughout the trajectory. And to get a better intuition about this from single neuron firing rates, so we performed this, so I'm showing you this PSTH, which is aligned to 2 time points, right? So here the neural activity is trial averaged. So on the left side, you see that the neural activity aligned to the onset of motion, and on the right, you see the neural activity aligned to the subsequent onset of licking. And the trials are averaged based on which well the animal is targeting, and the wells are color-coded. Now what you can see is that the well-specific or the location-specific neural activity pattern during the onset of licking is sort of replicated during the onset of motion itself, right? So this says that there's some information in the neurons about where the animal is going to go, even during the onset of motion. So of course, next we tried to decode, tried to see if we can decode the identity of the animal's goal from a population of OFC neurons. So we devised this decoding strategy where we take neural activity around the motion onset and lick onset and perform goal decoding on a cross-validated manner. So here is an example of a decoded trial. So the x-axis is time, y-axis is the position of the animal along the track. So the black line shows the position of the animal. And so before 0, the animal is at well 8. So here the animal is going from well 8 to well 4. So before 0, you can see that the animal is at well 8, then it starts running and eventually reaches well 4, right? However, if you look at the decoded well from the OFC population activity, at first it's well 8, then it switches to well 4 and stays there. And what's important is that the switch happens even when the animal is located at well 8, right? So this is like representing the future location when the animal is already, when the animal is somewhere else. And this is, I'm showing you some more examples from well 5 to 9, well 5 to 2. You can see the same kind of phenomena. And overall, when we group together multiple trial sessions in rats, we can see that the probability of decoding the goal well is significantly above chance, almost a second before the onset of the motion. Okay, so finally we wanted to, in this part of the project, we wanted to ask if the OFC is causally required for goal-directed navigation. So we planned to perturb the OFC activity by expressing this red-shifted channel rhodopsin and implanting optic fiber above it in the bilaterally in the OFC. And the idea was that if we perturb the OFC activity just during the start of motion, will the animal go to a wrong location subsequently? As opposed to if we perturb the OFC just before the onset of motion during licking. And what we found was that indeed when the OFC was perturbed at the onset of motion, the animals went to a wrong location 1/3 of the time. So this shows that the OFC both represents the goal and is necessary for goal-directed navigation. So which brings me to the second part of the talk about how does the OFC represent this relational aspect of these wells, right? Or in other words, can the OFC encode a topology-preserved map of this linear track? And for this part, we are going to focus on the neural activity around the onset of licking. So here, I'm showing you some PSTHs, which are, so the neural activity are aligned to the onset of licking, which is 0. And I'm showing you 3 different neurons from 4 different rats, right? And what you can see, so again, these are trial averaged and color-coded based on the well that the animal is licking. And what you can see is that there's an ordered nature in the firing pattern, right? So you see well 2 is more, so for example, in this cell, the firing rate in well 2 is very high, and then it's progressively lowering to well 9, and opposite patterns are visible, let's say here or here, right? And what is, so there, definitely these cells are kind of preserving the order in which the wells are there in the physical space. But there's also some nonlinearity, right? So for example, the difference between well 9 and well 8 here is much higher than the subsequent wells, right? So to understand what's happening at the population level, we projected the neural activity on the principal component axes, and here I'm showing you single trial data. So each squiggly line is one single trial, and it comprises 2.5 seconds of neural activity in that trial. And you can see ordered representations of the well emerging at the population level. Right, so here, so this was single trial, but when I do trial averaging, it becomes much clearer. So here you can see a really nice ordered representation, and it seems like almost that the spacing between adjacent wells is almost equal as seen in the real linear track. The only difference is that this lies on a curved manifold, unlike the real track, which is where the nonlinearities were coming in the single neurons. Right, now to quantify if these distances indeed are equal or not, I had to abstract out the temporal component, and for that we used tensor component analysis, where this is a tensor comprising neurons, trials, and time, and the algorithm squishes the tensor along each dimension, and you end up with this very useful thing called trial components, which is just a compressed, like a short vector that represents a full trial, right? So when you have these trial components, you can use them for visualization. So here you see each dot is a single trial, and you can see this nice ordered representation between the wells, of the wells on a single trial, on a single trial basis. And more importantly, you can use it for quantification, right? So because of the curved manifold, I use geodesic distance between trials. And here, if you focus on the upper triangular part of this distance matrix, each pixel is the geodesic distance between two trials, and the trials are ordered based on the well identity. And you can see that as you move away from the diagonal, the distance gradually increases, which is further seen, like if you actually plot out the distance, like if you regress the distance, the neural distance against the real distance, you get a near linear plot, right? Which means that the distances indeed in the OFC are almost equal among adjacent wells. Right, so this was from one session, but this is, I'm showing you sessions from 8 more rats. So this phenomena was actually quite replicable across rats. And finally, in the last 30 seconds, I wanted to say, like, does this map scale with distance, right? Or is it like a number line that just like encodes things in an order? And to answer this question, we used a large 4-meter track in addition to the 2-meter track, so the animal would do one session here and one session here. And so this is an example from one rat. You can see that the map formed in the 2-meter track is here, and the 4-meter track is shown here, and you can see that the map in the 4-meter track sort of expands out, right? And this is another example from another rat where you see that the map formed in the large track expands out. And if we do the same TCA-based regression analysis, now what we find is that the slope for the large track is almost twice that of that formed in the linear track, right? Which means that these maps scale with distance. So I showed you that the OFC represents the future goal and encodes a topology-preserved map of the environment that scales with the distance. And I would like, this work was mostly done in my postdoc lab in the lab of Hiroshi Ito, so I would like to thank the lab and the funding sources. And I just started my lab in LSAC. I'm looking for students and postdocs. So thank you, and I'll take any questions.
Thank you very much. We have time for questions. Yeah, shout. All right. Okay. Thanks.
So I had a question about the relation between the goal representation, the hippocampus, and the OFC. So we've shown several years ago in bats that you have, according to the direction and distance, to goals, and when you switch the goal, it switches to the new goal. So basically information about goal identity, direction, and distance is present in the hippocampus. Also, Keith showed something similar a few months ago, and also in OFC as we showed here. So how do these two brain areas do it together?
Right, perfect. So the work from your lab, actually, what we think is that that is downstream of the OFC, because in that paper you showed that the direction towards the goal and the distance were encoded, right, by the CA1 neurons. So we think that this is happening upstream. This gives like the actual location information, and the information seen in the hippocampus is more like a trajectory level information that is seen, which shows the distance and the direction. So yeah, you can think of this as upstream and the hippocampus as the downstream. So.
More questions? Okay, I have, yeah? Go.
Hi,
All right.
yeah, thanks, very interesting. So I was wondering, can you transform this into a kind of a probability spaces? Let's say you have like many goals now, right? And you need to calculate probability of different choices. So would this kind of...
Yeah, that's actually a very good point. So that's something that I'm actually going to set up in near future. So the idea is that what happens when it's not only space but another dimension as well, right? And what I think, what I hypothesize is that so the OFC in this linear track, you saw that it forms like a curved, essentially one-dimensional manifold, right? But now let's say you change the value along those spaces, like the different locations as well. So what I think happens is that then OFC would form a two-dimensional manifold, one that encodes space and the other that encodes value. And then the choices would be made on this two-dimensional space value combinatorial manifold. So yeah.
Great. Thank you very much, Raunak.
Thanks.